Hi everyone, this is a video to go over lesson 4.1, which is on maximum and minimum values of a function. Okay, so let's define what a maximum and minimum values are. The first thing we're going to define is a global maximum or minimum. These are also known as extreme values. Okay, so a global max or a global min is, so let's talk about global max first, the largest or smallest overall value of a function. I'm just going to write in blue here so it's a little bit different from the black color. Okay, so that's it. The highest point on a graph would be the global max. The lowest point on a graph would be a global min. These are also called absolute max, absolute minimum. Use the terms interchangeably. There we go. Okay. So absolute maximum is the exact same as global maximum, and absolute minimum is the same as global minimum. Depends on the textbook or the source you're using. They could be the same. They're the same thing. Okay, and there's also something called a local minimum and a local maximum. So a local minimum or a local maximum is the largest or smallest value of a function compared to nearby points. Okay. In the immediate vicinity. Note, some textbooks consider endpoints of a graph as they can consider them as local maximum or minimum, but for our textbook, they do not. So we're not going to be considering endpoints to be local maximums or minimums. We will not consider endpoints to be local maxima or minima. Maxima or minima, that's the plural version of minimum and maximum. Okay, let's look at some examples of what local and global minimums and maximums look like. So the first example here is a parabola. It has one global minimum. So the lowest point on the graph here occurs at x equals 0. So this has a global minimum. There is no global maximum or even local maximum for this graph, right? It doesn't have arrows here, but these go on forever. So this graph increases without bound to positive infinity. So there's no like maximum it ever reaches. It just keeps growing and growing. So not every function has to have a maximum or minimum point. This next function is y equals x cubed. It kind of levels off at x equals 0, but then it keeps growing again. And then as x gets negative, the graph falls towards negative infinity. So there's actually no minimum or maximum point here. So this function has no extreme values. Oops, there we go. And last, we have this function here. There's lots of points. So I'm just going to label them with my pen. Let's start at let's start with the maximums. So I've got two sort of peaks, right? This peak and this peak. This peak here is the largest point on the graph. You can't get any higher than that. So that is the global maximum. Sometimes I'm just going to say max for short because I don't want to keep having to write maximum. Okay, so that's the global max. And this point here is also a peak on this graph. If you look at the immediate vicinity around it, there's no other higher point, but it's not the highest point on the graph. So that's what we call a local maximum. I'll say max for short. Okay, so let's look at the minimum points or the valleys. I see 3 of them. So this is actually the lowest point on the graph. So that is a global minimum point. Global minimum points can occur at the endpoints. We just don't consider endpoints to be local minimum or maximum points. Okay. This is a local minimum. So in the surrounding vicinity or area around that point, there's no other lower point. So that's a local min. I like to think of them as peaks and valleys on the graph, right? And then this point here is again a local min. Okay, so this graph has a lot going on. It's got a global min at an endpoint. It's got two local minimums. It's got a local max here and then a global max here. Okay, let's look at a theorem related to these definitions, the extreme value theorem. We're going to be using this in the example on the backside of the notes. If a function is continuous on a closed interval, meaning you don't lift your pen, right? So the function might look something like this. Closed interval meaning there's two endpoints at x equals a and x equals b. Okay, so we don't not lifting our pen, there's two endpoints. Then the function must attain an absolute maximum and minimum value on this interval. Okay, so that's important. So if we know that you're not lifting your pen drawing this function and we're looking at a specific closed interval, then there is a local minimum or a global minimum and a global maximum. Let's look at another theorem here, Fermat's theorem. So when you have a local minimum or maximum at a certain point, and the derivative at that point exists, then the derivative must be zero. That's going to be really key for us. So in other words, you can't have a max or min where the derivative is not zero if the derivative is defined. So that means your max or min is always going to look like this. Okay. If the derivative is defined. Right, and there's always going to be that horizontal tangent line there. So the slope at that maximum or minimum point is always going to be zero. That's what this theorem is saying. Okay. So there are three different ways we can have a global maximum or minimum point on a closed interval. So this is how we're going to use the extreme value theorem. And Fermat's theorem. So we've got a closed interval in all three cases. We can see the solid points on either side of the curves. Okay, the first way we can have a global minimum is in this case here. Oops. Sorry, maximum. At x equals c, where to draw, oh well, global min max at f prime of c equals 0. So look at this point x equals c. Its derivative exists. I can draw the slope of the tangent line there. See how the slope of the tangent line is 0? It's a flat line, right? So this would be one scenario. This is one way we're going to be able to find our minimums or maximums, is that the derivative is going to be 0. Just want to highlight. There we go. Okay, let's look at the global minimums. The global minimum of this curve on is at x equals b, and an endpoint. So that's another place that these global minimums or maximums can occur. At the endpoint, the derivative is not defined, and so Fermat's theorem still applies. So it says if the derivative exists, then it must be 0. So if the derivative doesn't exist, then you can have a global min there too. So at the endpoint is another place where you can have a global max or min. Let's look at the next function. Over here, we've got, maybe I'll write above, global min at x equals 0, where f prime rho is, oops, is undefined. I'm trying something new with the typing. I feel like it's going to make my notes a little bit neater. There we go. Okay, so notice here we have a corner in the graph. So remember at corners, the derivative does not exist. There's no tangent line that can be drawn, so the slope of the tangent line is undefined. So that's another place where we can have a global minimum or maximum, is where the derivative is undefined. Okay, again, for this one, global max at endpoints. There we go. Okay. So again, that's another place where you can find maximums or minimums are at the endpoints. And then the last example here, both the global maximum and minimum are at the endpoints. I'll write that to the side. Max and min at endpoints. There we go, and change it to blue. Okay, so in conclusion, by looking at these three examples, we kind of found three important places we're going to look to find global maximums and minimums. One is at where the derivative is 0. That's where the slope of the tangent line is going to be 0, and usually that indicates a peak or a valley, but not always. Look at this last example here. At x equals 0, we have a slope of 0, but it's not a min or a max. So it doesn't necessarily indicate that, but sometimes it does. So that's one point. 2, the endpoints, and then 3, where the derivative is undefined. So there's going to be 3 critical points that we're going to look for in order to search for global maximum and minimum points. Okay, so that's what we're going to write down on the next page. If we're searching for absolute minimum and maximum, let's say we don't have the graph, so we can't just pick them out by looking at the graph. We just have an equation, let's say, and we don't know what the graph looks like. We can find the absolute minimum and maximum points by searching for critical numbers. So the critical numbers are possible places where these global minimum and maximum points are, and we just went over those 3. 1, where the derivative is 0. 2, where the derivative is undefined, maybe it's a corner or an endpoint, and 3, an endpoint. Okay. First thing you do is find all those critical numbers. Next thing you do is, by the extreme value theorem, the global maximum and minimums must exist. So you just test those 3, or test all the critical numbers, and the lowest is going to be your absolute minimum, and the highest is going to be the absolute maximum. Okay, so let's see what I'm talking about here by doing an actual question. So we're going to be finding the absolute maximum and minimum of this cubic function, x cubed minus 3x squared plus 1. So it's a polynomial. We're not lifting our pen. We can apply this extreme value theorem on a closed interval. Negative 1/2 is less than x is less than 4. So I'm going to have solid points at the ends of my graph. So I'm going to first write note, polynomials are continuous, so we can apply the extreme value theorem, EVT for short. Okay, so first thing we're going to do is look for our critical points. So those occur where the derivative is 0, the endpoint, and where the derivative is undefined. So let's find the derivative first. The derivative of our function is, so we use the power rule, 3x squared minus 6x plus 0. And I'm looking for points where this is undefined. It's just a polynomial, so it's defined everywhere. So the only places that I'm interested in are where this derivative is equal to 0. So we're going to search for points, find where f prime of c, and I'm using c for a critical number, so c stands for critical number. So I'm going to set my equation equal to 0. Okay, and just solve for c. So see if there's any c values there. So I'm going to factor. So I'll take out a 3 and I'll take out a c. So I've got c minus 2. And so there are two values where this is going to be 0 at c equals 0 and c equals positive 2. So those are two critical numbers. At those 2 points on the graph, my derivative is 0, and so they might be minimums or maximum points. Also, we have the endpoints. So negative 1/2 and 4. Endpoints are also critical numbers. There are no places where the derivative is undefined, so I don't have any of those to consider. In the next example, we will see some. We will see a point where the derivative is undefined. Okay, so that's step 1, find the critical points. Step 2 is to plug them into the equation and see where the min and the max are. So this is where you need your calculator. So I'm going to just plug in all three. I'll start with the lowest. And then I'm going to do f of 0, and then I'm going to do f of 2, and f of 4. So you're plugging into the original equation. So if you plug in, you can just believe me, or you can do it yourself just to make sure you understand. So if you plug in negative 1/2 into f of x, you get 0.125. If you plug in f of 0, you get 1. If you plug in f of 2, you get negative 3. And if you plug in 4, you get 17. Okay, so now we just look for the lowest and the smallest and the largest. This is going to be our global, oops. This is the lowest point, so global min. And this is the largest point, so global max. Okay, so then we just write a little sentence at the end. The global max, or you can say absolute maximum, occurs at 4,17, and the global min occurs at 2, negative 3. Okay, and so that's how you apply the extreme value theorem to find the absolute minimum and maximum. So I'm just going to go through one more time. First, you find critical points or critical numbers. Then there's 3 types, right? Derivatives 0, derivatives undefined, and endpoints. In this example, we only found 2 of those. And then you plug in all your critical numbers. The lowest is going to be your global minimum. The largest is going to be your global maximum. Okay, let's try it with a harder function, more difficult derivative here. In this example, I'm going to get a place where the derivative is undefined. Okay, so first step is to find critical numbers. So I'm going to find the derivative. It is a product, so I'm going to use the product rule to calculate this derivative. So first I do the derivative of the x to the power of 3 over 5. So this is the power rule. So it's 3 over 5 x to the power of negative 2/5. Let's make sure you can see the 3. Multiplied by the second term plus x to the power of 3 over 5. And the derivative of 4 minus x is just negative 1. So I'm multiplied by negative 1, or you can just say minus x to the power of 3 over 5. Okay, now we have to find which values this is equal to 0 or where it's undefined. In order to do that, we need to make it look a little bit simpler. And so what we're going to do is write this. First, we're just going to write it with only positive powers. So here we have x to the power of negative 2 over 5. I'm just going to put that in the denominator as a positive power. It'll just be a little bit easier to see what we need to do next. Okay. Next thing we want to do is try and write this as one fraction instead of having two fractions. Okay, so right now this term here is over 1. So if I want to make a common denominator so that I can combine the two fractions together, then it's much easier to figure out where this is going to be undefined and where it's going to be 0. So I'm just going to multiply by 5x to the power of 2 over 5 on both the top and the bottom. That way I'm not changing it, I'm just multiplying by 1, but it'll make a common denominator between the two fractions. So I'll have, and what I'll also do is expand this. That way it's going to be easier to collect like terms. So I'll have 12 minus 3x on top, 5x to the 2/5 in the denominator, and then here, when you multiply x to the power of 3 over 5 times x to the power of 2 over 5, remember when you have the same base of 2 powers and you're multiplying them, you can add the exponents. And luckily here, 3/5 plus 2/5 is 1. So that changes to just 5x in the numerator, and in the denominator I have 5x to the power of 2/5. Okay, now that they have the same denominators, I can combine them together and collect like terms. So I'll have 12 minus 8x all over 5x to the power of 2/5. Okay, there we go. That's much better. Okay, now I'm looking for my critical numbers. I need to find where this derivative is 0 and where it's undefined. Okay, so a fraction, it's going to be 0 if the numerator is 0, because 0 divided by anything is 0, right? So let's just write this here. When 12 minus 8c equals 0, that's going to be a critical number. That would imply the derivative would be 0, because 0 divided by anything again is 0. So if I just move the 8c to the other side, I'll have c equals 12 over 8, which reduces to 3 over 2, or 1.5. Okay, and then let's think about the denominator being 0. We're not allowed to have that, right? So anything divided by 0, that's going to be undefined. So when 5x, or I'll use c for critical number, 5c to the power of 2/5 equals 0, that's going to imply that my derivative is undefined. Well, that's equal 0 when c is 0. So that means c equals to 0. We're going to have an undefined derivative. I've also got 2 endpoints as well. So I've got 4 critical numbers. Just going to zoom out a tiny bit so we can see the whole thing. So here are my critical numbers. I've got my 2 endpoints, -1 and 4. I've got the point at which the derivative is 0, 3 over 2, and the point at which the derivative is undefined. Okay, again, if you have a fraction, the numerator being 0 means the entire fraction is going to equal 0. The denominator being 0 means the fraction is going to be undefined. Okay, so if your derivative comes out as 2 separate fractions, it's a really good idea to combine it into one fraction, and then you can find the critical numbers much more easily. Okay, I've got 4 critical numbers, just like in the first example. I'm going to test all 4. I'll start with the lowest one and make my way up. You can plug them in too. Some of them are going to be decimals. So you need a calculator for this. So -5, f of 0 is 0. This one you have to round it a bit because it's not a rational number, but it's approximately 3.19, and f of 4 is 0. So my largest one is going to be the global max, and the smallest one is going to be my global min. And I'll just write by typing the global max occurs 3 over 2, comma 3.19, and the global min occurs at -1, comma -5. I'm just going to show you what that undefined derivative point actually looks like on the graph before I turn this off. I'm just going to make sure my screen is being shared properly. Okay, there we go. I'm going to open Desmos. And just show you what that function actually looks like. So x to the power of 3/5. You don't need to know how to graph this, by the way. I'm just going to show you so you can get a visual. Okay, so the 3 points we had there were, oh, and this was only graphed on the endpoints, -1 less than equal to x less than equal to 4. Okay. I'm just going to put the 3 critical points down. So we had -1, f of -1. We had 0, f of 0. We had 3 over 2, f of 3 over 2. And we had, 4, f of 4. So you can see here, this is the maximum point at 3.19 approximately. This is the minimum point here at -1, -5. This was the point at which our derivative was undefined at 0, 0 here. So the graph is defined at 0, 0, but the derivative is undefined. That's because the slope of the tangent line at this point is vertical. It's completely vertical, and so vertical slopes, remember, are undefined, and so that's why that was a critical number. It's not a maximum or minimum point, though. And then here's our other endpoint, which is not a maximum endpoint either. Okay, so that's just a visual of what that graph actually looks like. So feel free when you're doing your assignment, you can use Desmos on the side just to like get a visual of what you're searching for. I always do that when I make your answer keys just to make sure I'm doing my calculations correctly as well. Okay, so the assignment's listed there, and that is the end of the lesson. Just turn off the recording.